Up to this point in time, you've been studying probability in the sense that it's an experimental one. And an experimental probability is one where we base our answer on what we see. So it is an observed probability of the relative frequency. So how many times we see an event occurring out of the total number of outcomes, or the total number of times that we've run a particular simulation. So we're going to contrast that with what we know to be true in terms of theory. So theoretical probability is what we're going to be investigating today. Okay, so if you look at the lesson objective here, you're going to be solving problems through this lesson, and with some practice involving the probability of an event for what we call discrete sample places. Okay, and the word discrete simply means that it is a number that you can count by. Okay, so for instance, the natural numbers 1, 2, 3, and 4. We can also use whole numbers, so 0, 1, 2, and 3. Continuous values or continuous sample spaces allow for a lot more numbers to be accounted for, specifically decimal values. So we can measure heights and weights to a certain number of decimal places. Those are continuous numbers. Okay, so what you're going to see before you is a fill in the blank, and it's just a bit of information here for you. So what I'm going to do is, if we were in class doing this, we would drag out this here, and you'd have all the information you need. So I'm going to read through, and if you find that you need more time to copy, remember this is a video. So you can pause, replay anytime that you need to in order to get your notes completed and to develop more understanding. Give yourself some think time. So the first nugget of information tells us that the theoretical probability of an event occurs when all the outcomes are equally likely. Okay, so for instance, if we're rolling a die, we'd want to know that the numbers 1 through 6 have an equal opportunity of turning up on any single roll of the die. Okay, so reading further, it's the ratio of the number of outcomes that correspond to the event compared to the total number. So if the event is rolling a 1, then the total number of outcomes being 6, the ratio would be 1 over 6. Okay. So moving forward here, looks like we are missing a term, so let's fix that up. So let's consider the simple event. Okay, now a simple event is simply an event where there's only one outcome that's being tracked. Okay, so for instance, you roll a die, what turns up? Okay, on a single roll of a die. So let's consider our event being rolling a number greater than 2. So using some notation, you can see rolling greater than 2, P standing for the probability. And with brackets, we generally read that as the probability of rolling a number greater than 2. So based on our knowledge, we know that's 4 out of 6, and 4 corresponds to the number of outcomes specific to the event, which is rolling a number bigger than 2, and 6 is the total number of outcomes. So in lowest form, we would say that's 2/3. Okay, so moving forward, there are a few definitions that we need to encounter, but I thought I would use your intuition in terms of getting them defined. So consider this activity. We have a Venn diagram before us. Okay, and Venn diagrams are simply graphical organizers for placing and categorizing information, which you would have used in the past. So I'd like to know, where would you place the following elements? And that is to say, the numbers we have here, where would you place them in terms of the diagram? And where would you place these labels in the diagram? So take a moment to consider the event, which is rolling a number bigger than 2. Consider all of the outcomes that we have, what you think the sample space might be, and what you think constitutes the event space. So take a moment and think about where you'd place those numbers. You might want to pause the video now because I'm going to reveal an answer. So give yourself that think time. So let's have a look at your solution. So you might have placed the 1 and 2 outside of the blue circle. Okay, that blue circle is known as the event space. So you can see how we have the numbers 3, 4, 5, and 6 falling in the event space because they are the outcomes specific to rolling a number greater than 2. The 1 and the 2 lie to the space outside of the event space because those are not what we're looking for. They are not desired outcomes. Okay, notice that the S is the sample space. The sample space is made up of all possible outcomes. That is numbers 1 to 6. The event space is simply a subset, okay, a smaller set that is embedded or placed within this universal sample space. Okay, so here's a few bits of information for you and some new notations. Again, I'm going to take these out and read them. I would recommend that you pause and copy, okay, and give yourself some time to think about it. So when I referred to the event space and the numbers 3, 4, 5, and 6, I would call that, or I would say that the number of elements, okay, n of a, okay, this means the number of elements in A, or in the event space, is equal to 4, right, given the 4 numbers. So reading further, the outcomes in that space are specific to rolling numbers greater than 2. On the other hand, when we look at the entire space or sample space, we're going to refer to that as n of s. Okay, so the number of elements in the sample space. That represents the total number of outcomes, in this case 6 possibilities for that simple event. Last but not least, because we're talking about probability and it is a ratio, a formula, which is very intuitive, we could come up with this quite easily because we've been writing ratios for quite some time. So the probability of event A is equal to the ratio of the number of elements in the event space compared to the number of elements in the sample space. Again, a little more information for you. When we consider all of the outcomes, especially their probabilities, so the probability of getting a number that's larger than 2, and also the probability of not getting it, we should take note that the sums of our probabilities are always going to be equal to 1. Okay, so in terms of a relative frequency, that's 100%. If we think about our probabilities in this example, we have already established was the probability of rolling a number bigger than 2 is 2/3. What I'd like to tell you now is that the term complement, okay, this is going to come into our work. The complement of an event is written as A, and this is an apostrophe here, so that's known as a prime. That's the name of the symbol, but we refer to that together as the complement, okay, of A. So it consists of all the outcomes in the sample space, but those that are not in A. Okay, so with that being said, we know that we are looking for the probability of rolling something less than or equal to 2. Okay, and that's equal to 1/3. The reason being, okay, stretch our imagination just a little bit. Recall that there are 2 values out of 6 that correspond to this criteria of rolling a number that is less than or equal to 2. Okay, so at the bottom, you might want to pause the video for now and consider these two problems, I'm going to go ahead and start writing in an answer or two to these, and then once you play it back, you can see if you've got the answers to them. So the first one says verify that the sum of all outcomes is 1, or that is the probability, okay, is 1 is how that should read. So if we're going to do that, then we're going to take the probability of event A, we're going to add on probability of the complementary event, and we'll take 2/3, and to that we'll add 1/3, and we end up with 3/3, which is equal to 1. So we have 1 whole. So we have verified that particular property for our example, and it does verify for all situations. Okay. The next question involves thinking of an event where the probability would be less than 0, or sorry, would be equal to 0, not less than. So is the minimum value for a probability, can it be 0? Well, what if we considered the probability of rolling a number on a single die that happens to be, let's say less than 1. Okay. Well, we know quite well in this instance that the probability of doing so would have to be 0, right? Complementary event would be rolling a number that is a discrete value, right? Not a continuous one. One that is greater than or equal to 1 would be 6 out of 6, which would be 1. And you can see how the first property, that the probabilities add to 1, is maintained even in question 2. So moving forward, just a little more information before you get into some practice. The idea of complementary events was brought up before, and now let's consider them in the context of something pictorial, like a Venn diagram. So I'd have you pause the video and go through the same exercise by placing the elements we have here, as well as these terms, into the Venn diagram below. Okay, well, seeing that you've got them placed now, let's check in and see if you've got the answers to this. So, much like we did before, the labels end up in the same place. The event space is still A, which is 3, 4, 5, 6 as the number of elements, and then 1 and 2 are still out there outside of A, but they're now occupying the complementary event space, because those are the outcomes that we're not looking for. You can see that all of the labels have been placed appropriately, and just a few bits of information. One of them being that the diagram might somehow be confusing or misleading in a sense. Okay, so for instance, the Venn diagram seems to show that the elements in the sample space might correspond to those in the complementary space. Okay, this is not the case. So what we're here to say is that the number of elements outside of A in the complementary space plus the number of elements in the event space together comprise all of the elements in the sample space. Another small formula, not that it needs memorization, but it is rather common sense that if we know the probability of something occurring, then the complement would be 1 minus the probability of that event. So with all of this information in hand, you're now ready to move forward, interpret some of the problems that you'll see through the textbook, and to get yourself thinking about calculating probabilities. So as an example, I'll leave you with this one. What I would ask you to do is, again, challenge your thinking. Pause the video, see what you can come up with, and then play it back to see what you've come up with. So, in part A, calculate the probability of rolling a sum of 7 when rolling 2 six-sided dice. Well, if you look at what we have here, just in this table, these are the possibilities for die 1. So the outcomes of die 1, here are the outcomes of the second dice. Okay. If we look further into the table, you're going to see that if we combine a value from die 1 with that of 1 from the second dice, we'll end up with a sum of 7. So for instance, on die 1, if I were to roll a 1, and on die 2 to roll a 6, then we can see how their sums are going to lead us to 1 of 7. So in total, you can see that we have 6 possible sums of 7 in rolling 2 die. So let's have a look at calculating the probability. So with our pen tool in hand here, in part A, probability of rolling a sum that is equal to 7 is going to be, let's practice the use of notation. The number of elements in the event space divided by the number of elements in the sample space. So if we look at what we have, already mentioned, we have 6 elements in the sample space, sorry, in the event space. And if you count them all up, we have a 6 by 6 grid, right? So 6 by 6, we have 36 elements there. So probability would be 1 on 6. The complementary event space, let's identify that. Complementary event space would be rolling anything but 7. Okay, a sum of 7, that is. So let's move forward and figure that out. So the probability of that occurring, what I'm going to do is I'm just going to clone this and bring that forward here into our calculation. I guess it's kind of overwriting everything else. I'm going to shrink that down. Perfect. There we go. Okay. I'm just going to scroll down and extend the page a bit to continue the work. So the probability of that occurring, anything but 7, is the complementary, right? So what we're going to do is we're going to take the probability of rolling a sum of 7, and from that we're going to take that away from 1, so 1 minus, so we're using that formula as shown previously. So we'll go 1 minus 1/6, and a little fraction work tells us that'll be 5/6, which is 6/6 minus 1/6, which is 5 out of 6. Okay, so in conclusion, therefore, the probability of rolling anything but a 7 would be 5 out of 6. Okay, so in terms of work that needs to be accomplished, okay, that ends this particular video. What I would have you do is check out the course webpage. See if we can go there now under Unit 1. And there is an assignment that is on page, I believe page 21, page 200, and let's see here. Here it is, 218. Okay, so 1 to 5, do any one of the first 5. Okay, pick one that seems to resonate with you, one that may be more interesting to you, and then 6 to 15 along with number 19 for tomorrow's class.